Hello, my name is Michael Drost, and I am the Secretary and Documentation Lead for this team. We are Team 5, and we partnered with Cascade Engineering to help them develop an insert load station. Shown below are photos of the rest of the team and their roles. Shown here on this slide are a couple photos of our final assembly. Cascade Engineering is a plastic injection molding manufacturer based out of Greater Grand Rapids, and they wanted some help developing a load station that could easily move inserts from an external to the robot cage inside, as well as be able to have a cart where you could move the PLC between the different molding presses and have the insert load station be modular so that you could change it out and use it for different projects. So these photos help show a condensed and more exploded view of those sub-assemblies. Just a quick cell operation flowchart. The operation starts by having the operator load the inserts into the insert load station. The insert load station or nest then poke yokes the inserts, and the operator will then push the nest forward into the cell. The robot end of arm tool will come and pick up those inserts using either a 3-jaw chuck or a slotted pin, and it will place the inserts into a mold and grab parts. While the mold is open, the end of arm tool will place the inserts into the mold, and then when the molding process is completed, the end of arm tool will remove the molded part. It then moves that part to the gate nip station, where pneumatics nippers will remove gating and pin prick the part. The operation then finishes by placing the finished part on the conveyor to be packaged then by the operator. The current system that Cascade currently uses is a non-modular setup. This can be seen in the top photo off to the right, and is completely fixed and confined to one molding press. It is not modular, so it can only run one product at a time and can be very time extensive into changing out those nests. It is difficult to slide the nest back and forth in between or into the cell, and the colored towers are used for poke yoking the inserts. And some examples of inserts can be shown in the bottom photo, and those are used to be put into the plastic injection molding presses. The current system also has a rat's nest of cables, which can be seen in the above photo, so they wanted that cleaned up. The current project objectives was to design and build a series of sub-assemblies. So the first one is nest fixtures for 2 different products that poke yokes the inserts. They also wanted a cage-mounted rail system for the insert load nest to be mounted to, as well as a mobile frame for all PLC components and controls to be mounted to. The last thing was an updated gate nipping station to remove excess material from the products. The first subassembly that we'll go over is the rail frame, and the key specifications for this subassembly was for the system to sustain a 100-pound force load with less than 0.04-inch deformation. They also wanted access to the PLC control panel while it was pushed into the rail frame, and it must accurately locate within the cell. There could also be no tripping hazards while the PLC cart was located within the rail frame. This is a view of that system. We can see a couple different components from it, as we have the front supports, which will be on the exterior of the cage. We have the center yoke, which will be coincident with the cage itself. There are also rear supports, all of which are fixed permanently to the ground. We also have a cable track to connect electrical wiring in between the PLC and the insert load nest, as well as a track support for that and a guide rail along the front of the rail frame to help guide the PLC cart in.
So this component is called the base plate and ejector system. It's composed of a series of 3 aluminum plates, which are connected by the 4 linear motion rods shown. This system is permanently fixed to the rail frame shown in the last section and is used to connect the modular fixture plates and allows the user to slide it in and out of the robot area. This component also acts as the ejector system for the pins which hold the inserts. And then if you go to the next slide, the guide carriages shown on the bottom mate with the rails on the rail frame and allow the user to easily slide it. So based on the calculated weight for the base plate and the fixture plate, it was determined that the resulting force required to push the system into the cage will be about 25 to 30 pounds. A custom pneumatic cylinder was required for the specific locations needed for the pins, which will actuate the dynamic plate in the middle to 3 separate positions based on the type of insert present. The cylinder has a 32 millimeter bore diameter, so it's going to have plenty of force, and the force can be adjusted on it. Finally, self-aligning linear bearings are attached to the dynamic plate in the middle, which will allow the plate to ride smoothly on the linear motion rods. And then other features you can see there include the fastener receivers that mate with the fixture plate, the safety panel, and then the solenoid locking mechanism, which is shown in red.
The insert load fixture design goal is to build a system where the inserts that can be applied to multiple products and allow for quick toolless changeover to make it easy for the operator. Some key specifications include poke yoking the inserts, so only the desired inserts would go into the fixture. It had to be repeatable within plus or minus 2 millimeters. Again, to have a toolless changeover. And we had to design fixtures for 2 different products using the same methods. That way, in the future, they'd be able to use those same methods to build more products. Here's a picture of one insert load fixture that we designed. The yellow blocks are on the nests where the insert gets loaded, and it is a sensor to sense that a insert is properly loaded. There are handles on each side for the operators. In 2 corners, they have quarter turn fasteners that make tools not required. In the opposite corners are tapered locating pins for precise locating. And in the back is an I/O module that the sensors would feed into, and that would be connected to the PLC. So then the system would know what product is currently loaded in the machine. It's a picture of our second fixture that we designed. This product only required 2 inserts, and they were different shapes, so the insert nest just had to be machined slightly different to accommodate for a larger size. We can see that we use the same methods here on a different product. Here's a close-up of how the nest operation works. Inside is a modified ejector pin that the operator will load the insert onto. You can see the sensor will sense the presence of the insert. And one design challenge we had was to how to accommodate it for whether the robot arm picks up the insert from the inside or the outside. So we designed it to do both using the 3-position cylinder that was shown. So on the left, we have the down position where the robot arm would grab the insert from the inner diameter. And on the right, we have the up position where the robot arm would be able to grab the insert from the outer position.
And for the gate nipping station, the scope of this part of the project was to design and build a system for the gate nipping nest that can be applied to multiple products and also allow for quick toolless changeovers. As you see on the left, that is a product that does not currently have a gate nipping apparatus for it. A runner, which is where that would be attached, would be removed by operators using cutting pliers or bending the molded assembly and breaking the runner at the gates, which is that location. And as you see, that is a visible defect that some customers may not prefer to see. And clean cuts using the gate nippers minimize the visual discolored plastic as a result of the stress. Key specs about the gate nipping station. The weight of the plate itself must be less than 20 pounds. Repeatability, the plate must be able to be placed onto the plate must be able to be placed onto the tower within 2 millimeters. Toolless changeovers for all electrical and air lines that are supplied to the gate nip station, and the runner must be cut at the gate, leaving little to no additional plastic on the final parts. The concept that you see on the left is a lightweight nest design for easy mobility. The nippers are oriented to remove the runner at the gate locations for a specific product. The handles are for easy mobility and increased control when carrying it around. Quarter turn fasteners, which are at the top and bottom corners to lock the plate into place during production runs, and also tapered locating pins, which will be located on the side corners to accurately and easily locate the nest on top of the tower. The base, which you see on the left, will be constructed from 2x2 inch 12 gauge steel tubing. Plastic totes will be placed in between the legs at the bottom to hold all excess plastic. The base will be mounted to a metal platen on the floor, so it will not move. And also there will be female mounting points on the top of the tower that will accept the male portions that are mounted onto the base plate.
Next, we have the portable cart, or also known as the PLC cart. The main problem description is to design and build a portable cart that moves key components from cell to cell based on the demand of the products at Cascade. Some of the key specifications for the cart is to have a toolless changeover, including all connections, have an ergonomic height of around 40 inches, emergency stop system, be user-friendly, and also take into consideration the operator safety. Here on the left is the design we came up with for the portable cart. Some of the key features are there's 3 ball plungers to help locate within the rail frame. There's the PLC access panel, a light indicator, it's mobile, an ergonomic handle, and a toolless changeover. Here's the control button assembly. So button wiring will be ran through the 2 holes, as you can see in the far left picture behind the plate. There's the light signal with wiring clips to help maintain wiring throughout the assembly, and then there's the light signal indicator to tell the operator what is happening when loading and unloading the inserts.
So the next subsystem is the controls, and the deliverables for the controls were to fully design a control system for the insert load station and the gate nip station, a complete PLC program, state diagrams for both stations, complete wiring and pneumatic schematics, as well as a bill of materials and quotes for all controls related components. The key specifications for the control system was that the machine had to be integrated with the control panel and an Allen Bradley PLC. The PLC had to be able to control both the insert load station and the gate nip station. It also had to be integrated with a method to automatically detect which product is running based on the current nest that was installed. It also had to be able to error or indicate to the operator when an insert was loaded incorrectly and they tried to run the machine. They also had to have a one-stop e-stop button for safety. It also had to have 16 usable inserts for the poke yoke sensors for the inserts, as well as have 16 usable control valves on the valve bank for the gate nippers. So the main considerations for selecting a PLC was the number of inputs as well as the number of outputs, and whether or not those inputs or outputs are analog. In this system, it's a completely digital system, so there was no analog inputs or outputs, which made selection of the PLC a little bit simpler. In this case, we went with an Allen Bradley Compact Logix PLC. This is a PLC that Cascade Engineering was already familiar with. This specific model has 16 digital inputs and digital outputs already embedded into the controller, which allowed us to connect the majority of our needed inputs and outputs into the controller directly. Since there is more than 16 outputs, however, we did need to install an expandable output card onto the PLC itself, as you can see on the lower right hand part of the screen. For the I/O link modules, one of the specifications was to figure out how to have the PLC automatically know which product was loaded or which product nest was loaded. And the way we're doing that is by using a Balif I/O link sensor junction box, and each one of the nests will have its own individual unique sensor junction block. And this sensor junction block will be used in conjunction with an I/O link master. The master will be installed in the control panel, and then the link, the sensor junction would be connected directly to the master. And since the sensor junction block has an application specific ID number that can be written to it and read from it by the PLC, whenever you plug in a new sensor junction block, the PLC will be able to read that application specific ID number and therefore know which plate is installed currently. One of the other specifications was to indicate to the operator the status of the machine. We're doing this by using a stack light in conjunction with a touch to light button. So certain lights indicate the certain statuses to the operator while they're running. And also you can see on that picture below, there's a one touch e-stop button, very easily accessible. Here are some examples of the schematics. On the left, you can see a power distribution schematic. In the middle, there is a panel layout. And on the right, there is a pneumatic schematics for all the control valves for all the different gate nippers and ejector position cylinders. Here are some programming examples. On the left is an example for the program that was programmed in ladder logic, as well as on the right there is a state diagram for the insert load station. So some of the project modifications that were made due to COVID-19 include working remotely. We all had to communicate over software such as Google Meets. We also were not allowed to build the actual machine due to hazards of COVID-19. That part of the build will now be performed solely by Cascade Engineering. A large part of the scope of work that was altered during the second semester of our project was to accommodate much larger bolted pieces. And that included us changing our design to accommodate a much larger area for inserts to be loaded. It was a 12 by 12 inch area that you could potentially have inserts loaded. Now it is 22 by 22, and changing a lot of the design for that. Thank you for your interest in our senior design project. If you'd like to ask more questions or you'd like to see more CAD of the whole design, I invite you to come to our virtual design day. It is on July 31st between 2 and 3 p.m.